Hello everyone, this lecture video is all about calculating the net ATP production from the complete oxidation of fatty acids. So I have mentioned in the previous lecture, right, that the new acyl-CoA produced in step 4, this one, will undergo a repetitive cycling process in which there will be no acyl-CoA produced, only the acetyl-CoA. So how will you know how many times should the process be done? This one is an pathway for stearic acid, and the formula for stearic acid is C18 H32O2. This is the chemical formula of stearic acid. So from this observation, this is an 18 carbon fatty acid. So to determine how many times should it be repeated, should a cycle be done, or should the steps be done, this is the rule to determine the number of repetition. So the number of repetition of the beta oxidation pathway that are needed to produce the acetyl-CoA is always one less than the number of the acetyl-CoA molecules produced. And how you will know how many acetyl molecules will be produced? So the number of acetyl-CoA molecules produced in the beta oxidation pathway is equal to half the numbers of carbon atoms in the fatty acids. So I have mentioned here that the stearic acid, this is for a stearic acid, is a C18 molecule or 18 carbon molecule. Mean to say the acetyl-CoA that will be produced from that is half of the number of the carbon atoms. So if that is 18, the carbon present, so 18 divided by 2, that will be 9. Right? 918. So, meaning to say there will be 9 pieces of molecules of acetyl-CoA that will be produced here in the process. And then, how will you determine, again, the number of repetition that will occur? It is -1, the acetyl-CoA that has been produced. Because the last step, you will no longer have an acyl-CoA. So, that is -1 of the acetyl-CoA that has been produced. So, 9 minus 1, that is 8. So, we should do the steps 1 to 4, 8 times. So, let us count. That is 1. Steps 1 to 4, that is 1. And then each loop here in the pathway represents the repetition of steps 1 to 4. So if this is 1 from this stage, 2, 3, 4, 5, 6, 7, and 8. So that is the number of repetition of steps 1 to 4 in order to produce acetyl-CoA. And there will be no acyl-CoA that will be produced in the process at the end. And then if you will notice here, you will have decreasing even numbers in terms of 2. So C14, C12, C10, C8, C6, C4. So how does that happen? So from step 1 here, you will have C18, right? Step 1. I have mentioned that here in step 4, this is -2 of the carbon because the acetyl-CoA here is -2 from the acetyl-CoA that will be produced. So -2 you will have at the end of the step 4, you will have the C16. So that is why here in the loops here, at the end of the second repetition, you will have a C14 plus acetyl-CoA. At the end of the third repetition, you will have a C12. Of the fourth repetition, you will have C10. And then at the fifth, you will have carbon 8. And then 6, you will have carbon 6. Then at the 7th repetition, you will have a carbon 4. And at the 8th repetition, you will no longer have an acyl-CoA. Instead, all of the carbons here had been converted into acetyl-CoA. Okay, so that is the process for the stearic acid. Now, let us calculate the net ATP production for this one. Okay, for stearic acid, that is C18 H36O2, right? So, the number of acetyl-CoA is half the number of the carbons. We have 18 carbons, so therefore 18 divided by 2, you have 9 acetyl-CoA. And 1 acetyl-CoA will produce 10 ATP. So, you will put the 1 acetyl-CoA at the bottom so you can eliminate that unit. And you will multiply that here because 1 acetyl-CoA is equivalent to 10 ATP. This is the convention. Okay, or dimensional analysis for that. So 9 times 10, that will be 90 ATP in acetyl-CoA. And for the reduced form of the flavine adenine dinucleotide, you will have 8 pieces of flavine adenine dinucleotide in this process here. In this one. Why? Because, so we said that the number of the reduced form of flavine adenine dinucleotide and the reduced nicotinamide adenine dinucleotide that is produced will always be 1 less than the number of acetyl-CoA that has been produced. So if this is 9, so that is -1 here. 9 minus 1, that will be 8. And 1 reduced form of flavine adenine dinucleotide will produce in the electron chain transport 1.5 of the ATP. So 8 times 1.5, that will be 12 ATP. Of course, you will cancel the units here and you will be left out with the ATP unit. So the value of the reduced flavine adenine dinucleotide and the reduced nicotinamide adenine dinucleotide is the same. If this is 8, this is 8 as well. So 1 NADH will produce 2.5 ATP. 8 times 2.5, that is 20 ATP. And if you will add that, that is 122 ATP. But we have to subtract 2 ATP because in the fatty acid activation, we consume 2 ATP, right? If you will remember, we consume 2 ATP in the activation or in the bonding of the coenzyme A in the free fatty acid. So, that will be your ATP from the fatty acid activation. You consume 2 pieces of that to inorganic phosphate, and the ATP had been converted into AMP from the previous lecture. So, this is minus 2 here. Therefore, this gross production of ATP here must be decreased by the ATP needed to activate the fatty acid. So, that is minus 2. You consume 2. So, therefore, the net ATP production for this is 120 ATP. Okay, and then another example, sample problems. What is the net ATP production for the complete oxidation of fluoric acid, a C12 fatty acid? The chemical formula of fluoric acid under the microscope is C12H24O2. So this is a 12 carbon fatty acid based on this presence of carbon. And we have to calculate how many ATP will be produced from that. So let us start here. Okay, so we used 2 pieces of ATP in the fatty acid activation. And then for the production of acetyl-CoA, since that is 12, half of that is acetyl-CoA. So 12 divided by 2, that is 6. And 1 acetyl-CoA is equivalent to 10 ATP. So you will cancel the units here. 6 times 10, that is 60, plus 60 ATP. And the next, the production of the reduced flavin adenine dinucleotide. This is always 1 less than the number of acetyl-CoA that has been produced. So, 6 minus 1, that is 5. Then, therefore, 1 reduced flavin adenine dinucleotide is equivalent to 1.5 of ATP. Okay, so you will cancel the units here. 5 times 1.5, you will have 7.5 ATP produced in reduced form of flavin adenine dinucleotide. Now, for the reduced form of nicotinamide adenine dinucleotide production, you will have 5 NADH, that is NADH, that has been produced. Why? Because that is also 1 less than the number of the acetyl-CoA that has been produced. So, 1 NADH will produce 2.5 ATP, so cancel the unit. And 5 times 2.5, that is 12.5 ATP here. So, if we will perform this in calculator, that is 78 ATP. So, the net ATP production from the complete oxidation of fluoric acid is 78 pieces of ATP. So, now let us determine how many repetitions or how many times should the process step 1 to 4 be repeated in order to completely oxidize the lauric acid. So this is a C12 molecule. So we have mentioned here that the number of repetition of the beta oxidation pathway that are needed to produce the acetyl-CoA is always 1 less than the number of acetyl-CoA molecules produced. So if this is a C12, so half of that is acetyl-CoA, so that is 6. And the number of repetition is 6 minus 1 acetyl-CoA produced minus 1 as always. So, meaning to say you have to repeat the beta oxidation pathway 5 times. Meaning to say the loop that you will have here is 4. 1, 2, 3, 4. Because you will have fifth process. And then let us have another example. I have here, what is the net ATP production for the complete oxidation of palmitic acid? This one is a 16-carbon fatty acid. The chemical formula of that is C16H32O2. Okay. So, how many acetyl-CoA will be produced? So, that is half of this one. Okay. So, that will be 8. There will be 8 acetyl-CoA. And 1 acetyl-CoA is equivalent to 10 ATP. So, cancel the units. 8 times 10, that will be 80 ATP. And let us calculate the production of the reduced flavin adenine dinucleotide. That will be 7 because that is always 1 less than the acetyl-CoA that has been produced. Okay. So, 7 times 1.5 because there will be 1.5 ATP at 1 FADH2. So, cancel that. 7 times 1.5, that will be 10.5 ATP. And let us calculate here the production of the reduced nicotinamide adenine dinucleotide and palmitic acid. So, that is the same numerical value here in FADH2 because that is always 1 less than the acetyl-CoA produced. So, if you have 8 here, minus 1, that will be 7. And 1 NADH is equivalent to 2.5. So, cancel the units. 7 times 2.5, that will be 17.5 ATP. And we will subtract 2 ATP here because we consumed 2 pieces of ATP in the fatty acid activation before the beta oxidation pathway, before we transported it inside the mitochondrial matrix, if you will remember. So that is minus 2 ATP. So if you will perform that in your calculator, the total net ATP production in palmitic acid is 106 ATP molecules. And how many times should the beta oxidation pathway be done? So, if you have here 8 pieces of acetyl-CoA minus 1, meaning to say we have to perform the beta oxidation pathway 7 times. Meaning to say you will have 7 loops here. 1, then 2, 3, 4, 5, 6, 7. 7 loops. Okay. Let us compare the complete fatty acid oxidation and the complete glucose oxidation. So, one glucose will produce 30 ATP based on this lecture that I have taught you. And then, one stearic acid, this one here, where is that? Will produce 120 ATP, minus 2 because of the fatty acid activation. You will have here 120. And then, 3 glucose will produce 90 ATP and 1 stearic acid will produce 120 ATP. Therefore, we can conclude here that the lipids are 33% more efficient than carbohydrates as storage energy systems. Okay? Let us discuss the comparison between complete oxidation of fatty acids and complete oxidation of glucose in terms of equal mass basis. So, when we say equal mass, we will assume a 1 gram of each, 1 gram of stearic acid and 1 gram of glucose. Let us determine the moles of ATP that will be derived from this one. So, when we say moles, if you don't have your Chem 1 and Chem 2 in senior high school, that is the amount of quantity present in a molecule. So, I have here 1 grams of stearic acid and you have to get the moles of that in order to be converted that into ATP. So, in 1 mole of stearic acid, there are 284 grams of stearic acid. This is based on the calculations of the molar mass, this one. So, the formula is C18H36CO2 or C17H35CO2 hydrogen. Okay, I just compressed the formula O2. Okay, so the atomic mass or the molar mass of carbon is 12.0107 atomic unit, mass atomic unit or atomic mass unit. And then the hydrogen is 1.00784 atomic mass unit or molar mass or grams per mole. And then the oxygen is 15.9994 grams per mole or atomic mass unit. So you have here 18 pieces of carbon because you have here 17 based on the subscript and 1 carbon here. That's 1. So 17 plus 1, that's 18, and you will multiply that into the molar mass, okay, or in the atomic mass. You can find this in your periodic table. So, multiplying that, you will have 216.1926, and the hydrogen is 36 pieces because you have here 35, plus 1 here, that is 36. 36 times 1.00784, the atomic mass unit or the molar mass or the atomic mass of hydrogen, is equivalent to 36.28224, and then the oxygen, you have 2 pieces here, so that is 2 times the atomic mass of 15.9994, that is 31.9998. And if you will add that, therefore, the molar mass of, in terms of grams, molar mass is also equivalent in grams. That will be 284.47364 or just 284. So you will have here the grams of stearic acid at 1 mole is 284 grams. And you will convert that into moles in terms of ATP. 1 mole of stearic acid will produce 120 moles of ATP based on here. Where is that? Isa pa. This one. Okay, 1 mole of stearic acid will produce 120 ATP. Okay, remember that? So, let us proceed here. This one. Okay, and let us cancel the units. Numerator to denominator, and then numerator to denominator. You will be left with the mole ATP units. So, if you will perform that calculator, 1 times 1 divided by 284 times 120 divided by 1, you will have 0.423 moles of ATP here in stearic acid. Now, let us proceed on the glucose. So, you have to convert that first into moles. Okay, to convert it into moles, the grams should be placed at the denominator in order to cancel the unit. So, the 1 grams of glucose, you will multiply that in the number of grams present in 1 mole of glucose. And in 1 mole of glucose, you will have 180 grams because this is the chemical formula for glucose. And the value of the carbon is 12.0107. You have 6 pieces of that. Multiplying that, you will have 72.0642. Then the hydrogen, you have 12 pieces here. 12 times 1.00784. Multiplying that, you will have this value, and then the oxygen, you have 6 pieces of that. Multiplying that, you will have this value, and if you add that, you will have the molar mass of 180.1154 or just 180. So here you will now have the 180 grams per mole of glucose. So cancel the grams unit, you will be left with moles, and 1 mole of glucose is, you will have 30 moles of ATP based on this lecture, 30 pieces of ATP here. Okay, and then you will cancel the units, moles of glucose, you will be left with the moles of ATP. So, if you will multiply that, okay, cancel. So, 1 times 1 divided by 180 times 30 divided by 1, you will have 0.167 mole of ATP. So, if you will observe here, in terms of equal mass basis, the stearic acid or fatty acid is still greater than the glucose here. So that is why fatty acids are much better energy storing molecules than glucose, because if you eat only 1 grams of fatty acids, you will have more energy compared to when you eat glucose. Some of the uses, I will reiterate again. The skeletal muscles uses glucose from glycogen when in active states, and in resting state it uses fatty acids. Now the liver uses fatty acids as the preferred fuel as well. So that is all for the calculations of net ATP production from the complete oxidation of fatty acids.